All right, everyone, we'll go ahead and get started now. Again, apologies for the delay here this morning. I mentioned a few of you got on here after I probably mentioned that we've had a bit of a comms outage here at the office, and so I'm on a MiFi, so hopefully this works, and hopefully you can hear me just fine. I'll be answering questions at the end, of course. And then also I will, hopefully I can show some examples of some recent events as well. So thanks for joining on today. We'll go ahead and get started. This is a kind of a Doppler radar interpretation presentation for everyone, for emergency managers primarily. I'll be recording this presentation and hopefully getting it up on YouTube so that we can share it out as well. So what are we going to cover today? Well, for the most part, we're going to cover an introduction to basically how the radar works. Some of you this might be a refresh, basic radar imagery, interpretation basics, some radar limitations. There's limitations to the data, and then some classic storm structures as well. This is a map of the basically continental United States, the outlying areas of the United States, Alaska, Hawaii, Puerto Rico, some Pacific Islands, basically where we have WSR 88Ds. Those are the big radar. If you've been to Pleasant Hill, you've seen our radar here at the office. That's us right here in the middle of the country. This is the coverage map showing bottom of beam coverage below 10,000 feet above ground level. So as most people know, we do have a little bit of a 10,000 foot gap up there in north central Missouri and northeastern Missouri. And we'll talk about how that impacts some of our operations as well. So we have two radars in our backyard. We have the 88D here in Pleasant Hill. We have the terminal Doppler radar at KCI. Our radar here at the office, the 88D, is a 10 centimeter wavelength S-band, which means it's a long wavelength radar. There's 155 total NWS radars, along with the DoD FAA. We share responsibility of control of the DoD radars, but they have maintenance responsibilities. A lot of those are related to the Air Force bases. The reason why our radar is where it's at here in Pleasant Hill is because of where Whiteman Air Force Base is and Kansas City proper. We're right in between the biggest population center and the Air Force Base for proper coverage for them. The terminal Doppler radars came about after some incidents, the most famous being the downburst incident at DFW that resulted in a plane crash. These are 5 centimeter wavelengths, so smaller wavelength radars. They're C-band, which is short wavelength. These are at most airports across the country. In Missouri, we have 2. We have one here at KCI, then we have one at St. Louis. And the pros and cons between the two, of the 88D and the TDWRs, is the fact that the TDWR is a short wavelength, which means it has a more attuned to attenuation. So this example is from the Dallas-Fort Worth area. So the image on the left is the Fort Worth 88D, so the Weather Service radar at the Fort Worth office. And then you have on the right side the terminal Doppler radar at DFW. If you notice, it is a higher resolution radar, the TDWR. However, it cannot, once it basically, the beam, because of its short wavelength, doesn't have the penetrating power that the 88D does with its 10 centimeter wavelength. So you lose resolution behind whatever higher returns you're hitting. So it's hitting all the more reflective and more stronger storms along that line, but it's missing all of the lighter rainfall behind it to the west of the radar location. So these are some pros and cons to the TWR. So I mentioned our radar here in Pleasant Hill. This is a picture of it from not too long ago. This is a video of the dish inside. Hopefully it plays okay. I might play it a couple times. So inside that dome, inside the golf ball, there's a pretty large dish, and it is counterbalanced, weighted, and on a motor, and it spins around. It's operational 24 hours a day, 7 days a week, 365 days a year. We do take it down for maintenance, and sometimes we do have some issues where we have to do unscheduled maintenance on it if it goes down, and usually our techs are pretty fast about it. We even have to change the oil in the gear set. So it's a moving piece of equipment that's constantly moving and actually moves at a fairly powerful clip when we're in our fastest scanning strategy when it's running. So how does the radar work? Well, most of you are probably well aware of how it works, but It's a call and response. So the radar sends out a microwave pulse, and honestly, it does this in fractions of a second, almost the speed of light does the initial pulse come out of the radar. And then it listens for basically the return. So whatever it's interacting with in the atmosphere, and the weather radars are designed to operate basically as a call and response, but they're designed to operate with hitting smaller targets. So we're not going to pick up airplanes, we're not going to pick up anything like that. It's tuned for hitting smaller objects such as raindrops or hail or other items such as that. So I mentioned the radar is a call and response. So as the radar antenna turns, it emits an extremely short burst of radio wave, which we call a pulse. Each pulse lasts about the speed of light. Every pulse is 1.57 times 10 to the negative 6 seconds. It happens, I mean, just like that. So between each pulse is a listening time frame, which is a much longer period of time where it listens for the return signal back to the radar. This process is repeated nearly 1,300 times a second. But actually, and each pulse goes out with a transmission power of nearly 450,000 watts. To put that in perspective, an average household microwave is about 1,000 watts. Because of how fast this process occurs, the radar is only on, sending pulses for about 7 seconds per hour. So in an hour, even as fast as this process occurs, the pulse coming out of the radar is only 7 seconds per hour. The rest of the 59 minutes and 53 seconds, the radar is actually listening. So there isn't just this continuous, beam of microwave energy coming out of the radar. It is actually spending most of its lifetime listening for those return signals. So again, I mentioned the weather radars are tuned for different targets, and its potential targets are the general things we think about: rain, hail, snow, and drizzle. However, given the time of year, we can pick up dirt, it can see smoke, we pick up wildfires all the time. We can pick up chaff sometimes from the Air Force if they're doing training missions, insects, birds, any kind of density change in the atmosphere, whether it's a temperature inversion or an increase in humidity in the air, it might pick up those density changes as well. And I'll talk a little bit about what that looks like later on. Okay, so we'll talk about the different volume coverage patterns. We call these VCP. So the radar isn't just set to one standard and then it just continually runs. We actually have a set of strategies that we use the radar, and I'm going to talk about the 3 general scanning strategies that we use and most weather service offices use across the country for varying reasons. The first one is clear air mode. That's VCP 35. So clear air mode has, 2, 4, 6, 8, 9 elevation scans it's going to make. This takes about 7 minutes to complete on average. If it's winter time, we'll use VCP 31, which is basically it's more sensitive, and it's a longer pulse, and we can actually listen for a lot longer, and we get more fine details. So if we're dealing with snow, also snow is not normally a rapidly changing situation. We'll use VCP 35 or VCP 31, and it's about 7 to 10 minutes for those scans to come back, but it gives us a high resolution reflectivity that we want to see, so we can see the snow and the ice crystals in the atmosphere. Then we have our general precipitation scanning strategy, which is VCP 215. And this one has a whole host of, basically we'll go up to as high as a 19.5 elevation scan. We also have a program called AVSET, which I'll mention in a second, that explains kind of how we can shorten the duration of this. But this takes only 6 minutes. We got more scans, but it takes only 6 minutes. And the reason why is because the dish is spinning at a much faster rate. So we're trying to get as much information as we can. However, that also gives us a little less resolution. So there's always trade-offs to this. So the VCP 35 is a longer duration scanning strategy. The dish is moving at a slower speed. It is sending out a longer wave pulse. It's listening for a lot longer for high resolution. VCP 215, it's moving much faster, about 5 to 6 minutes. And that's so we can see things quicker. Because if we're in a thunderstorm situation or a general precipitation system, that's going to be rapidly evolving faster than a snow situation would be. So that's why we want to have a faster scanning strategy. The one we'll use the most for severe weather mode, that's VCP 212. Again, this one has a highest elevation scan of 19.5 degrees elevation. And this one can take approximately 4.5 minutes. Again, faster scanning strategy, but we lose a little bit of resolution because of that. But we also want to know what's happening a lot faster, because a lot can happen in a thunderstorm in 4.5 minutes. But that's also why we have a program called AVSET, which is Automated Volume Scan Elevation and Termination. So basically, AVSET, it's all automated, and we can turn this on or off. Most of the time, most offices will keep this on. So it ends the volume scan early, so cut anything above 5 degrees elevation if the radar is no longer detecting 30 dBz of reflectivity, less than 30 square kilometers, and also 18 dBz, less than 18 square kilometers. So if it's not detecting anything up there, there's no reason for the radar to be scanning that high anymore. It'll cut it, drop the scan back down to a half degree, and start a new volume scan. This gives you a visualization of kind of what those elevation angles look like from the radar. So this is just a cut across section of the radar data, and you can see those each individual scans. Most of you on here know that the radar doesn't work like we see in movies and TVs, where there's just sweeping beam going across and it's picking up everything at once. It actually takes time. So it does the first scan at half degree, and then it goes up to 2.9, then 1.3. It keeps going up and up and up. And then again, if we have AVSET turned on, it goes, oh, I'm not reading anything, I'm not getting any returns anymore. It'll cut off the scan and we'll start back over. So an entire volume scan is the collection of all these individual angle cuts from the radar. So in the last 10 years, we've had some new scanning strategies come into play. Even though the 88D and the 88 and 88D stands for 1988, technically, nothing inside that radar is from 1988 other than some of the physical, the pedestal itself, which has been refurbished about 3 years ago. If you remember, we had the dome taken off and had a new pedestal put on, new dish, everything was refurbished. That was a service life extension program that the Weather Service had to get us into the 2030s with the radars. These things are much more advanced than they were when they were deployed in the late 80s and early 90s. And the Pleasant Hill radar was originally deployed in 1993 and 1994. This radar is much different than that radar was 30 years ago. So SAILS stands for Supplemental Adaptive Intra-Volume Low-Level Scan. And basically what it means is that the radar starts the lowest elevation, half degree for us here at Pleasant Hill, scans up through the sky for about 2 minutes, and then after scanning the middle elevation, the radar will go back down again and give us another low-level scan. And then it'll return back to where it was in the middle elevation to finish the rest of its volume scan. We can do a SAILS 1, 2, or 3, so we can get 3 low-level scans, and this gives us the potential for a half degree low-level scan every minute. So if we're concerned about tornadoes, if we're concerned about QLCS, spin-ups on the line, this is a perfect example of why we would use SAILS in those situations. So again, without SAILS, 3 to 4.5 minutes for a full volume scan as the radar beam starts to fill out its entire volume scan. But with SAILS, it'll go maybe about 2 to 2.5 minutes. It starts out at half degree, goes up to 1.8 to 3.1, somewhere around there, and it'll drop back down and do another half degree scan. And then when it's done with that half degree scan, it'll go back up to where it was, about 1.8 to 3.1, and then start over and then finish out the rest of its scan. So I'll talk a little bit about, we also have I will say real quick, and I don't have a good example of it here, but we also have another scanning strategy called MERL, and it gives us extra mid-level scans. So if we're more concerned about hail, we can actually get an adaptive strategy where we can get more mid-level scans. So we can see the middle of the mesocyclone. So you see more of the hail growth zone within the storm, which gives us a better idea of what type of hail sizes we might be dealing with and might need to be warning on. So now I'll talk a little bit about Doppler radar images. Obviously base reflectivity, or Z, which is the dBz. is what most of you are familiar with and what most people see on TV or on your radar apps, places like that. So this is generally what it looks like from our point of view from the office, from our radar in Pleasant Hill. This was the Linwood EF4 tornado, started south of Lawrence and made its way into Johnson and Leavenworth County and Wyandotte County. So what is reflectivity and what do the colors represent? Well, reflectivity is how much the outgoing signal is returning to the radar. And the amount of reflectivity depends on the size of targets, the density of those targets, and the types of targets. The highest reflectivity comes from a rain-hail mixture or from non-meteorological targets sometimes. And think about the reason why a rain-hail mixture might be the highest reflectivity is if you take an ice cube out of an ice box and you let it melt for a little bit, it gets real shiny, and the radar is gonna be higher reflectivity or higher reflective property. So the radar signal hits it and then bounces back, goes, this thing's pretty hot, it's a high reflectivity. It'll give us those whites and purples and pinks on the radar for the highest reflectivity. Because the energy return to the radar is proportional to the number of targets and the diameter of those targets. Therefore, a 1-inch diameter hailstone will reflect 1 million times more energy than a 0.1 inch diameter raindrop. So let that settle in for a second. And from radar reflectivity, we can also infer kind of the rainfall rates per hour. So this is another product we can get from the radar. But again, this can be skewed by hail contamination within the radar itself. We have some algorithms to try to help to change that or kind of limit that. But generally speaking, if you're looking at 30 to 40 dBz, you're looking anywhere from 1/10 of an inch an hour up to 1/2 inch an hour. And then once you get 50 dBz and 60 dBz returns 2.5, and then it goes up pretty fast to 12.9 inches an hour rainfall rates. So I will say that the radar color scales are kind of the same for most. Our defaults are usually the same, whether it's a TV example or your radar app, or even here at our office, our default scales. But however, we can change the color to whatever we want. So we have some forecasters in our office, one that's colorblind, and it's like, well, how can you be colorblind and be a meteorologist? Well, he's not fully colorblind, but his radar color scales are a little bit different. This is the Grain Valley QLCS tornado from last year that went up. You might remember it hit that mobile home. It hit the trailer and RV center there along I-70 and pushed a trailer down into the drainage ditch between I-70 and the dealership. This is an example of kind of the way that you can change the color scales and the velocity images to give you a different look at what the circulation looked like. So I grabbed these from our science and operations officer because he is the colorblind person in our office, and this is what his color scale looks like for velocity so he can see better. Traditionally, the velocity images are red, and red is away from the radar and green is toward the radar. So I've got the radar here on the right-hand side of the screen to show you where the Springfield radar was. This is the Joplin tornado, what it looks like on reflectivity. Again, Joplin is 70 miles away from the radar site in Springfield, and Springfield radar is the nearest radar to Joplin. So this circulation, you're actually looking at the mesocyclone, not technically the tornado at this time, because you're probably about 7,000 feet off 6 to 7,000 feet off the ground. But it was such an intense tornado that you could pick out this velocity signature really easily. And at this point, the inbound velocities are so strong, they're actually blue in color and the almost orange on the outbound signature. So I'm going to talk a little about composite reflectivity now, because this is something that we see a lot and is shown a lot on large radar maps, especially on television or even on the Weather Service web pages. So composite reflectivity can give you kind of a skewed view of what you're looking at. It actually takes the highest reflectivity from the volume scan and then puts that onto the map. So it tends to obscure your low-level features. It might inflate the intensity of a thunderstorm. You're going to lose your hook echoes, your inflow notches, but it does give a quick overview of kind of your precipitation intensity. So there are some uses for composite reflectivity, and usually it's a broad overview, but not really for looking for close-in structures. So be careful when you're using radar apps or looking on TV. If you see composite reflectivity, you're not getting the highest resolution data, because this is an example of the base reflectivity from Fort Campbell, Kentucky. If radar, this is what the composite reflectivity looks like. So you notice it's a little more darker in the reds through the main line of thunderstorms. You also have greater coverage of kind of the darker greens and lighter greens. So I'll go back and show it. So this is your base reflectivity. So just your half-degree low-level scan. And this is your composite reflectivity. So it's grabbing the highest reflectivity, the highest dBz from any of the volume scans and putting them all into one composite image. So another example, this is the Memphis base reflectivity from the Memphis radar from a series of storms, and the composite reflectivity from the same time frame. So be careful when you're using data or looking at data that if you're looking at composite reflectivity, it may skew what could be the intensity of the entire line of storms, and you're going to lose those low-level features. We also have some beam height sampling issues. So the white line here from the Goodland radar out in Goodland, Kansas, through this area of thunderstorms kind of basically gives you a rough idea of what we're going to be cutting through. So I'm going to show the cross section now along that line of these storms. So the radar in Goodland there on the bottom on the left-hand side, and then you notice that the base elevation of you can see where the half-degree scan goes out off the horizon, we lose data in the lowest levels. So when you're all the way out away from the radar, you're looking at 11,800 feet at the base of the storms you can see. You're not going to be able to see anything below that. Your radar data also becomes basically the beam becomes wider, and so you're actually losing resolution also the farther you go away from the radar. So I'll talk about the cone of silence here too. The cone of silence is basically everything above the radar you cannot see. So if you go up to the 19.5 elevation cut on VCP 212, the severe weather mode for the radar, if the storm is really close to the radar, like this example is here, this image, this illustration, you're losing all of this data. You're not going to be able to see it with the radar. So if this is the radar in Pleasant Hill, and we have a storm over the office, we're going to have we're basically not going to have a picture at all of what the storm looks like. When we have storms over Pleasant Hill or close to the radar here in our office, we'll actually use the Topeka radar to get an idea of what the mid-levels and high levels look like, because that's our nearest radar to us besides our own. And then also it doesn't have this radar hole over us or the cone of silence. So here's another cut through the Goodland radar to kind of illustrate the cone of silence. And again, storms really extend up through here up to 30 to 40,000 feet. You just lose all of this information, which is why it's important if we have storms moving towards your radar and you're using a radar app like Radar Scope, or you're using GR Analyst on your PC, you're going to notice that as the storms get closer to the radar, other than your low-level scan to see it like circulations, you're losing the extent through the column of the actual thunderstorm. It might be a good idea to switch over to another radar, and for us, it might be Topeka. If you're in central Missouri, it might be St. Louis. If you're down south, it could be Springfield. We're constantly looking at our neighboring radars to really get a good idea of what's going on aloft in the storms. So real quick, just kind of for fun, what is not the cone of silence? Well, a lot of people think that this circle here around the radar is actually the cone of silence. And when you're looking at the plain view like this, that's not correct. So recall the radar works as a call and response. The radar basically shouts out its beam and then it listens. It's the Doppler part of the Doppler radar. And this all happens again in microseconds, almost in the speed of sound, that this beam goes out and it listens for another couple seconds or microseconds. And in general, the time from the shout to the listen takes about 7 microseconds in total. So from the time it yells, the radar shouts out, it's about 7 microseconds before it's able to hear again. Again, nearly the speed of light. So get a little cheeky here. We know the speed of light is about 670 million miles an hour, almost 671 million miles an hour. And the speed is distance and time. Then the math says that in 7 microseconds, the pulse will have traveled about 1.3 miles before the radar can actually listen. And that's what that hole is. That's what the radius of this actual physical hole is on the images of the radar. So if you actually look at it and go, it's 1.3 miles. So that's not the cone of silence, that hole. That's just the time. That's just the gap between the listen and or the call and response of the radar. I just think that's kind of fun and a fun fact for everyone. So this is your call and response hole on either side of the radar, and then this is your cone of silence, everything above that the radar cannot see. So we also have some challenges with the beam width. So nothing's perfect. Think of the pulse as a cylindrical volume, and keep in mind that there's actually a 1 degree beam width. So that's why the beam goes out at a half degree. The center of the beam goes out at a half degree usually for most radars. It's because it fills up the whole 1 degree beam. Now the Earth curves away. The radar is angled a little bit up. Again, it's angled upward, I should have mentioned, because we don't want to run into things downstream, and if we have trees near the radar, things like that, we have to get above it. So the beam width determines the resolution or blockiness of the image. So the beam widens by about 1,000 feet every 10 miles. So at 100 miles, the beam width is about 2 miles. And that's why we lose that resolution as we get farther and farther from the radar. And generally why most of the 88Ds, their really serviceable range is about 200 miles away from the radar. So here's an example of beam width resolution issue, the beam width / resolution issue. So we've got storms over Goodland. We're looking at the Dodge City radar. And if we're looking at the Dodge City radars on top, and this is the city of Goodland here in the middle of the screen, storms around Goodland, Kansas. Well, if you look at it from the Goodland radar, much higher resolution. But from the Dodge City radar on top here, lower resolution. Same thing here. Here's storms over Dodge City at the top, high resolution. But again, you're missing things aloft due to the cone of silence. And then here's what they look like from the Goodland radar. Low resolution, much more blockiness, less defined. Beam blockage issues aren't too much of a problem in our office here in Pleasant Hill. We don't have anything near the radar that really causes a concern. But I'll talk about it anyway, because this is possible. It's either due to terrain, a lot of times it's trees. A famous one is the Vance radar in northern Oklahoma. There's a series of trees on private property, and there's full-blown beam blockage. That radar needs to be a little bit taller. As those trees grew, it kind of blocks the beam. So here's an example from Albuquerque. You have the mountains just to the east of Albuquerque, and that is the beam blockage here off the low-level scan. So you get around this by looking at a higher, you can go up to 0.9 or 1.3 degree scan to get over the mountains. As I lost internet today, for those that have joined late, as we lost the internet here in the office and I'm on a MiFi, I was trying to grab some better examples of purple haze or range folding. So you might see this sometimes in the velocity data, and this is range folding is a common problem with pulse Doppler radars. It's the Doppler dilemma is what we refer to it as. So basically, when the radar transmits its pulse and it hits its target, but it cannot get back to the receiver before the next pulse is transmitted, you're going to end up with this we call range folding. You end up with this purple haze here. And this is due to the pulse repetition frequency. So we can adjust the PRF to push it farther out or closer for the initial range for velocity. However, the farther we push it out, the less resolution we get with the storm. So there's this dilemma there between, especially if we're dealing with tornadic storms, we don't want too high of a PRF or we're going to lose resolution in the circulations in our velocity data. So we'll do our best to try to cut down on range folding, but oftentimes with storms and things going on, it can rear its ugly head, and we usually try really hard. So if you're ever in NWS chat / Slack and you see one of us chatting there, like trying to take care of the purple haze on the radar, we're really more than less talking to the TV meteorologist to let them know that, hey, we know this is a problem. We're trying to get it rectified so that when they're live on the air, they're not showing some messed up velocity data. We'll try to adjust that from the radar through our control system for the radar here at the office. Didn't grab an image of this, but we've all seen this, anomalous propagation or ground clutters. So usually with the lowest scan, it occurs in meteorological conditions where the signal comes back to the radar in the absence of precipitation. Most commonly occurs with super refraction. This is when the radar beam hits a temperature inversion, so when temperatures increase with height, and then the beam bends back toward the surface. So we might pick up bugs or might pick up migrating birds. If we have a density change, a lot of times we'll talk about fine lines on radar, like we can see the cold front on radar. That's due to the density change in the air behind the cold front, and then all the dust along the leading edge, we can start picking up in the radar and we can see it on radar. So this one is, I'll try to keep it pretty basic, but vertical side lobe contamination has become more and more of it became the bigger challenge when we ended up with dual polarization of the radars. So vertical side lobes are commonly seen in the low levels and from the overhang with elevated thunderstorm cores. So when the radar beam goes out, remember it's a cylindrical pulse. Well, the main center of that beam is the strongest signal from the pulse. And then you have this drop off on the sides, and the main lobe goes out, and then you have your side lobes of the same cylindrical beam. Sometimes the side lobes will hit a higher return from an overhang of the core, like an overhanging part of the thunderstorm, and then that ends up producing a false return back to the radar. And this rears its ugly head when it comes to circulations. So we can actually, it looks like you've got maybe a tornadic circulation or a rotational circulation in the storm, when in reality, it's actually a data artifact of the side lobe and not reality. So I'll try to kind of visualize this here. So this image on the left here at the top, the graph, this is the main power from the middle of the beam. So imagine this whole thing from negative 12.5 to 12.5 degrees is one basically pulse of the beam. Your main power is in the middle here, and then you have these side lobes, or the side lobe of the beam. This is a visualization of it here down below as well. So when that main lobe fires off from the radar, and here's a thunderstorm, the lobe is cylindrical. So the main power source, the main power of the beam is the middle, but you might end up getting these kind of weaker side lobes of the cylindrical part of the beam, the pulse going out. It might send back some bad data. So what happens is it's an imposter circulation. So some things you can do if you're looking at stuff and you see red and green next to each other, don't immediately assume, oh, I've got a tornado. It could end up being one of these side lobe contaminations. And again, they happen more than you think. And this image here on the left kind of shows that you have this really nice hook echo and the reflectivity. But if you notice, where you would expect to see the circulation would be within that hook echo. But in this example, it's displaced. It's positioned farther to the right of the hook. So, that's actually the inflow region and your outflow and your forward fake downdraft. This is a problem. So there's been false alarm tornado warnings issued for this by offices because they didn't notice that this was offset and there was something off about this. So you can also tell from the texture of the circulation or the velocity pattern. So notice that this image at the top is a circulation, likely tornadic circulation. See how smooth that is and how easy the transition is? It looks, even a static image, it looks like it's rotating. But if you look at the imposter version below, it's more blocky. There's no clear gradient in the velocities. They're just right starkly next to each other, the inbounds, the blues, and the outbounds, the reds. So that's one way you can tell is that how blocky this is and not how how fluid this transition is in the upper example. And then if you look at through a cross section, a 3D version of this, if you see something like this, you're like, I think there's something wrong with this velocity image, and you have GR, you can do a cross section through it, and you can actually see the overhang of the storm, and that's where that beam is hitting, and it increases your confidence in the imposter circulation. We take this very seriously in the office, and we will look for these pretty closely. And if we think there's side lobing contamination, we'll try to let you know about which storm that is in Slack and chat, so that you're not caught off guard like, well, I see the circulation. Well, it may actually be side lobing. So we'll talk about some radar signatures here real quick. Most organized supercells we'll talk about first. They're the most organized thunderstorm, single rotating updraft, almost always severe, high threat to life and property. Most tornadoes come from supercells. So this is if you've seen the spotter training class this year, I've thrown this in here, and this is the schematic of a supercell looking top down, and the main parts, your updraft region, the UD, the rear flank downdraft, the drier mid-level air wrapping around the storm, and your forward flank downdraft where the rain and hail are falling out. This, again, from 1979, adapted from Lemon and Doswell. Dr. Chuck Doswell and Les Lemon drew the schematic of the first supercells. And they look like this on radar for the most part. You have your hook echo. You can infer the rear flank downdraft wrapping around from the mid-levels down in the drier air, hence the lack of reflectivity here. And then your forward flank downdraft where your rain and hail is falling. All of this, where you have your higher reflectivity returns. This is also a supercell. The first one here is the Auric tornado from, I believe, 2014. And then this is the Linwood tornado from 2019. Also a supercell, high precipitation supercell. Your RFD is actually obscured by rain. A lot of moisture in the atmosphere, a lot of activity going on here. Still a supercell, still a hook echo, still your forward flank downdraft and your rear flank downdraft. This is the Linwood tornado in a loop. Again, classic looking signatures on radar. You have your circulation there. Again, it looks very fluid. You're not worried about side lobing. It looks the way it should. It's positioned within the hook echo where it should be. A good view of what a classic supercell looks like. There's also tornado debris signatures we can see from this. Now, before the advent of dual polarization of the radar, you'd have to have a really strong tornado to get a tornado debris signature. You have to get debris lofted very high in the atmosphere. But now with correlation coefficient, the dual polarization now allows us to understand more of what's going on inside the with the radar. We can actually infer these drops in uniformity of the objects the radar is hitting. So instead of hitting uniform objects like raindrops, we know that it's hitting ununiform objects such as debris. So you get this drop in correlation coefficient, which is usually a blue image like that. So squall lines and shelf clouds, from this example, the storm movements from left to right. Your shelf cloud is where you infer your warm, moist air inflow into the storm. You have your rain, cooled air blowing out the bottom. The shelf cloud equals the leading edge of the strong winds. So as soon as that shelf passes over, you're going to get hit by the strong winds here. The strong winds of the outflow is the forcing mechanism for the inflow region of the storm. Generally what they look like on radar, this is a composite reflectivity, or we talked about composite reflectivity earlier, of a squall line moving across Missouri, Illinois, and all the way to Indiana. Another example of a multi-cell squall line, what they're going to look like. Your shelf cloud will be right out here, leading ahead of the area of reflectivity, because your shelf cloud is not where it's raining back behind. So your shelf cloud will be out here ahead of it. Similar to multi-cells and squall lines, again, if you look at velocity, you have your strong outbound velocities from the St. Louis radar, which is right here, St. Charles County. You can infer even the inflow with the green inflow inbounds out ahead. This is an example where the outflow boundary is now surged out ahead of this line of storms. But you can see the multi-cell features along the actual line itself. This line here, this leading edge, where the density change is, is why you're picking up this dust and debris dust that's being blown down from the outflow. Your shelf would be actually along this leading edge. And this is it in motion. So squall lines usually have a pretty simple life cycle. The bow echoes and part of that is a bow echo as it develops. You end up with your initial set of thunderstorms developing usually along a low pressure center or boundary. They continue to travel, and as they travel, they end up creating their own outflow and their own basically maintenance. So as long as the rear flake, the low-level jet pushing in behind continues to maintain balance with the inflow, you end up developing this line into a more robust line, and then over time, you can end up with these circulations along the line, and sometimes you end up on the bookend, what we call a bookend vortex. So this is an example of the way a bow echo looks as it pushes in. You have a real strong rear inflow jet pushing in from behind. You can actually see the outflow boundary right in here. This is unbalanced line at this point with the outflow pushing out ahead. But up here, you're much more balanced where the stronger rear inflow jet is, and you start to see, you can infer kind of the bookend vortex begin to form circulation on the northern edge. Similar thing here, you have a real strong rear inflow jet. That's where your drop in reflectivity is. You have well-balanced line out ahead. You cannot see a line of outflow racing out ahead. And then sometimes if you get on these vortexes can develop into a QLC, what we call a QLCS tornado or a squall line tornado. And we've talked about these ad nauseum in spotter training classes, but for the most part, it's an enhanced pocket of wind, or you do have a small tornado there along the leading edge. And so as these lines push in, you might end up with this kind of embedded EF0, EF1 tornado along with the damaging straight line winds, and you have more of an enhanced path of winds, usually lasting maybe a mile, 2 miles at a time with these storms. We had a very similar event happen last year in Johnson County, Kansas, where we had several embedded circulations on the line. Some of them did not create a tornado and some of them did. It's just a matter of the fine scale dynamics going on at the surface that even we can't resolve on radar. I'll talk about winter real quick just for kicks. Winter radar images look a little different. So again, as I mentioned at the beginning, we usually use the clear air mode, or VCP 35 or 31, which is the slowest of them, but the highest resolution, because snow is a slowly evolving event, not a quick evolving event like a squall line or a bow echo or a supercell. So with the winter images, you get kind of this fine scale detail, and it almost looks a little feathery on the edges. It's because of the ice and the way it reflects, the way the return is received by the radar from hitting ice. And so it looks a little different on radar. It has more softer edges, not as starkly defined as raindrops, but it gives you an idea of what that kind of looks like. Usually your higher returns are heavier snow, but then also you can end up with bright banding. So this is melting snow, and actually this is looking at probably a 0.9 or 1.3 degrees elevation scan. You'll end up with this bright banding right here, and it's usually a melting layer aloft, resulting in melting snow. Similar to melting hail or rain-hail mix, you get a higher reflectivity with that. And so if you start to see bright banding or start to see basically 40 dBz returns in snow, it's more than likely melting snow through the melting layer. You can also, from that, kind of deduce, is it rain, is it a mix, is it snow? If we know there's a melting layer and it's melting completely, then you could have snow aloft, and if we finally are able to cool the column completely below freezing, you end up with all snow. So you can kind of infer from where the rain and rain snow mix and snow are occurring on the radar. So I will kind of wrap this up with a little bit of like where we came from. So the old WSR 57Cs were repurposed Navy radars. The Weather Service first deployed back in the 1970s. Back then, we also had to, well, I didn't have to, but I worked with some people who used to have to do this. Grease pens and transparency sheets with maps, and that's how you would track storms over time. Now things are much different. The 88D, again, even though it's almost over 30 years old now, the internal components and all the technology with it is all the way upgraded for today. Much more robust system, much better radar data that we're getting back to the office. So we went from here at the beginning with the 88D using what they called the PUP to interrogate storms and issue warnings, to now we have AWIPs and we can interrogate storms much quicker, much faster, get warnings out the door much quicker. We have higher resolution data. This is super res data from the early 2000s to now with the higher resolution data with dual polarization. So dual polarization has made a huge change to the things we can see on radar now. Instead of having just horizontal pulse, we now have the horizontal and vertical pulses. So I'm gonna stop sharing my screen here for a second and share my other screen, and I'm gonna pull up some radar images from the Friday night event from March 14th down in Springfield and one from St. Louis. So give me 1 second here. So let's look at St. Louis first. Well, you guys can see this. So this is we'll talk a little about the Bakersfield tornado. So to orient yourself, this is the Missouri-Arkansas border. You have the Springfield radar here in Greene County, and then you have the Bakersfield storm. It's going to be an EF3 tornado right now. On the right here, or on the left here, I have reflectivity, and on the right here, I have standard velocity, base velocity. So we're looking at here from the radar to Bakersfield, we are at 73 nautical miles, and we are about 5,000 feet above the ground. So this circulation we're looking at is 5,000 feet above the ground. That's a pretty significant circulation. Very easily a tornadic circulation given the conditions and the environment. But this gives you an idea of what it looks like in real time of what you'd be looking for. Now, along with this circulation, as it went through Bakersfield, let's back up to the beginning here. I'm going to put this into 4 panels. Excuse me. And I'm going to add a correlation coefficient to this. Bottom. Spectrum width here. Spectrum width is a good judge of how turbulent air is. It's 0 to 4, these darker purple colors, the air is pretty uniform, but as you get into the stronger colors, the base of the airflow is less uniform. So as we move forward, I'm sorry for the jumps here. You have the tornado going through Bakersfield, and on the backside, you actually can see this right here on the correlation coefficient, lower left-hand side. That is your debris signature. And you can see it almost carry on to southward before it dissipates. So that's the Bakersfield tornado, kind of way to look at it. We'll look at the St. Louis one next. So we're going to focus on the storm that went through Franklin County first. And I will grab my 2 panels to start. Your base velocity. And I'll actually use what we call our storm relative velocity for this one. So I'm going to get our storm motion. So storm relative velocity is basically, you can set your storm motion for the radar, and the radar will do a calculation. Let's see. It won't let me set it. Storm motion from marker. Come on. Sorry, this is what happens when you lose your internet before doing the before leading a class. So your tornadic circulation is actually right in here, going just kind of north of St. Clair through your inflow. This is a supracellular structure, of course, embedded along a line with other supracellular structures. You can actually see the circulation start to move in toward Union, and then it actually cycles a bit. You get new inflow, and then you get a secondary circulation through Villa Ridge right here. This storm wrapped up and continued through St. Louis County. And then as it moved across a very populated area from Chesterfield to Maryland Heights, ended up crossing the St. Louis airport, which I don't have the data all the way out, but ended up going all the way through, and then I've lost some data in my download. But this is an example of where this continued on. So there were several tracks from Union through St. Louis and up through Florissant. I apologize for the internet outage, kind of throwing this off for me and having everything ready, but gives you an idea of kind of what we look at and how we use the data. So let's see. So that I'll take any questions. I appreciate you all logging in today. Hopefully this was useful. If you want to type in any questions below, you can, and I'll be more than happy to answer them. So thanks again, everyone. I'll try to record this and get this up on YouTube and share it out with you all.